All right, so this is a two-part talk. So what I want to do is explain a little bit about some of the problems in L functions, give you an example of how you would do some of these calculations for the n-level densities, and talk a little bit about some of the families I hope we will look at this summer. Okay, so the first is, why study zeros of L functions? So it turns out that there's a lot of problems we care about in number theory whose solutions are related to properties of L functions. So the first is, are there infinitely many primes, or primes in arithmetic progression? Another great one is Chebyshev's bias, that when you look at numerical tables, it seems like there are more primes that are 3 mod 4 than 1 mod 4 as you start counting. Another is the Birch-Swinnerton-Dyer conjecture, that the order of vanishing of an elliptic curve L function at the central point is the geometric rank of the group of rational solutions. So this is the geometric rank equals the analytic rank. Another one is, it turns out that there are bounds for the class number that are related to finding L functions that have many zeros at the central point. This is where elliptic curve L functions come into play. And I'm not going to go into too much detail on stuff like this. If you haven't seen the class number, it's a very important quantity in algebraic number theory. So how did the distribution of zeros help us with questions like this? Well, the first is, if the Riemann zeta function does not vanish on the line real part of s equals 1, then we get the main term for the prime number theorem. And similarly, for generalizations of the Riemann zeta function, we get the primes in arithmetic progression. If we have some estimate about how far away we can be from the real part of s equals 1 and still have no zeros, then we get better error terms. And the Riemann hypothesis is that we can go essentially all the way down to real part of s equals 1/2 without finding a zero. And that gives us essentially square root cancellation in terms of the error. The next is the grand simplicity hypothesis. Have any of you heard of GSH? So for those who Riemann is not nearly enough, where you want even more about the zeros of your functions, the grand simplicity hypothesis says that the zeros of your L functions are linearly independent over the rationals. Because, how could there be any relationship between them? Well, except maybe if you have vanishing at the central points. You have to throw that away. But other than that, all the zeros are independent over the rationals. It turns out that that is one of the key statements that we need in understanding Chebyshev's bias as to why there are more primes most of the time that are 3 mod 4 versus 1 mod 4. You need a certain flow to be equidistributed on some space. And if you look at, let's say you look at multiples of an irrational number alpha. If you look at n alpha mod 1, if alpha is irrational, that's going to flow uniformly in the interval 0, 1. If alpha is a rational number like 1/5, well then n alpha mod 1 you get 1/5, 2/5, 3/5, 4/5, 5/5, which is 0, 6/5, which is 1/5, and you just cycle through those values. So the GSH, the fact that they're algebraically independent, and that they're linearly independent over the rationals, gives you a certain flow is well distributed. Okay. So the goals is very similar to what we did before, is to see the correct scale. Probably won't say too much because we just had a talk on that. See similar behavior in different systems. Not going to talk too much about that because we already did classical random matrix theory. Discuss the tools and techniques that we need, and talk a little bit about some of the proofs and some of the families. All right, so you've seen the slide before on the different questions we study. The 3 things we need to do. What's the correct scale? We need some kind of averaging formula. And we need some kind of explicit formula. All right, so I'm going to skip all the random matrix theory. The nice thing about, I can't do it here, is I could actually click on any of these circles and just jump to that point. My computer's now too far away for me to actually do the clicking, but introduction to L functions. So the Riemann zeta function, the most important function you will look at. It's defined as the sum of 1 over n to the s, where n ranges over the positive integers. It turns out by unique factorization, it's the same as the product over primes of 1 minus 1 over p to the s inverse. What is the closest prime to 2017? 2017, yeah, we're actually a prime year. What's the next prime after 2017? What's the next integer? Right. There really is not that much mystery in the distribution of integers. We really have a great understanding. And in fact, we have an explicit formula for how far you have to go from one integer to reach the next integer. Okay, primes are much different. Much, much harder to understand primes. So the goal is to take the Riemann zeta function, with this representation where we understand things about integers and convert it to information about the primes. So it has a functional equation, and this is where you use some complex analysis. So this completed function, it turns out its value at 1 minus s is related to its value at s. It has a really nice connection. What this means is we only have to understand what's going on for the real part of s greater than or equal to a half. And then by this functional equation, we understand it elsewhere. The Riemann hypothesis is true, but we don't have a proof yet. All the non-trivial zeros have real part 1/2. And then the observation is that the spacings between zeros appear to behave the same way as various families of matrices. And the question is, why is this true? For the Riemann zeta function, it's a bit mysterious. For other families of L functions, you can relate things to monodromy groups and have some understanding of why this is happening. Well, instead of studying the Riemann zeta function, you can study more general L functions. And you can see there's not that much of a change in these slides. Rather than having a 1, you now put these numbers AF of n. You can put anything you want. Just most of the time it'll be useless. We typically want something so that we have an Euler product. So we can represent this as a product over primes of some local factors. There will be some kind of completed functional equation, basically shove in some stuff over here, and then you relate its value at 1 minus s to s. One of the things that you need to be extremely careful about is normalization conventions. We've already talked that the Fourier transform has at least 3 different ways of normalizing things. You can normalize L functions many different ways, and depending on what L function you're looking at, you may not want to normalize it in the standard way. It's nice to have all L functions have functional equation relating s to 1 minus s. So all L functions have critical strip from 0 to 1. All L functions have the center of their critical strip at a half. For elliptic curve L functions, if you're only looking at elliptic curves, it's actually more convenient to look at things going from 0 to 2. The problem with this is if I give you an elliptic curve L function, and I'm talking about what's going on at s equals 1, is that at the edge of the critical strip, or is that at the center of the critical strip? It's not clear. So sometimes people just say, look, let's just always have our L functions go from 0 to 1. It's a simple change of variable. It's then clear what's going on. But it introduces certain normalizations that make some problems a little bit messier. Certain things would be an integer, but now they'll be an integer divided by the square root of an integer. So you just want to be aware when you're looking at things, what convention are they using? And so all the non-trivial zeros also have real part of s equals 1/2 in this normalization. All right, so here's the first really nice plot showing what's going on. So this is by Andrew Odlyzko. He looked at 70 million zeros starting at the 10 to the 20th zero of the Riemann zeta function. So this is one of the master computers. Why do you think he's starting at the 10 to the 20th zero? Yeah, smaller zeros, the limiting behavior may not have set in yet. And so if you go down to the 10 to the 20th zero, you've gone pretty far down. But we hope it's far enough down to see what's really going on in the limit. And it's an incredible fit between the eigenvalues of matrices and the zeros of L functions. We actually have a theory now for the distribution of the fluctuations between these two systems. You can't see the fluctuations on this scale, but you can subtract predicted from observed. And we have an understanding of these lower order terms, and that's something I've been talking about in the past. All right. So if you take any math class with me, you learn to have a Pavlovian response whenever you see a product, right? Whenever you see a product, you should take a logarithm. Possibly the only exception is if you're volunteering in an elementary school and you're helping little kids multiply 7 times 8. Well, the log of 7 is this and the log of 8 is that. Then we add them and then we take the anti-log. No. Other than that, take logarithms. Why do we like taking logs of products? Because it gives us a sum. You've all done summation theory. You've done Riemann sums. We know how to handle sums. Almost no one has taken a class in advanced product theory. It doesn't mean we can't do it. It's really the same thing, but we just have more experience, more familiarity with sums. Let's convert things to sums. So in complex analysis, it turns out you want to take the logarithmic derivative. So if I take the logarithmic derivative, that gives me basically zeta prime over zeta. It's more convenient to have a negative sign here, not a big deal. And that's the same as the log of the product. And this is now why we care so much about the product expansion of L functions. We had the sum, and we had the product. Why is the product so nice? Well, when we take a logarithmic derivative, we now have a sum coming out of this. That's very nice. And so we get the following. And so now I expand the log of 1 minus p to the s. I can use the geometric series after I take the derivative, and I get the first term, and then everything else I'm going to call it good of s. It's not that bad to deal with. And it turns out that in complex analysis, we have really good ways to integrate zeta prime over zeta, or just the integral of f prime over f. Complex analysis is all about evaluating integrals like that. And so we can get information about this quantity, and we'll use that to get information about the primes. So explicitly, we'll integrate against x to the s over s. And if you've done complex analysis, we'll do a contour shift, and you get a contribution over the zeros and the poles. This is a sketch of the proof of the prime number theorem. Zeta has a pole at s equals 1, so you're going to get a contribution of -1 because it's a pole. Negative times negative is a positive. You'll get an x. And then you have an x to the s over s at every 0. And if the Riemann hypothesis is true, that's going to give you things of size square root of x. And this is where the lower order, this is where the error term is coming from. And so the larger the real part of a 0 is, the larger the error is going to be in your prime number theorem. On this side, we now have the integral of x over p to the s ds over s. It turns out this is an easy integral to do. This integral is 1 if p is less than x, and it's 0 if p is greater than x. So you can think of this as a detector function, as an indicator function. It detects whether or not p is less than x. I'm sorry? Yeah. And so over here, this is going to just count how many primes are there at most x. Notice that we're weighting the primes by a log. You could remove this with partial summation, but the log really belongs here because when we're doing the logarithmic derivative, we get a log of p that comes out. So that's the natural quantity to look at. When you want to count how many primes there are up to a certain number, you don't really want to count the number of primes up to x weighted by log p. But the quantity that you want to study, how many primes, that's not the natural quantity to count. The correct quantity to count is the weighted one, and then you remove the weights. Okay, well, instead of using x to the s over s, I could use some function phi of s. And so I'll get phi on both sides. So now what I'm going to be doing is I'm going to get contributions, the zeros and poles over here. Well, what about this side? Well, I'm going to write p to the minus s as e to the, so p is the same as e to the log p. So this is e to the negative s log p. I write s as sigma plus it, and you can see basically this is a Fourier transform. It's a Fourier transform of a shift of my function phi evaluated at a log of a prime. And this is going to give you a sense of the explicit formula. This is playing the role of the eigenvalue trace lemma. Okay? And so explicitly, if I were to calculate things for the Riemann zeta function, I end up getting something that looks like this when the dust settles after I do complex analysis. This is the analog of the eigenvalue trace lemma. You could do it for Dirichlet L functions. So for Dirichlet L functions, I have a character chi of n. And so how many of you have not seen Dirichlet characters before? Okay, excellent. So I have a Dirichlet character, so it's multiplicative. Chi of AB is chi of A, chi of B. If I have a character to a prime modulus, I have a nice generator. And we'll talk a little bit more about this later when we get to the explicit calculations. And so I now have some formula like this. And so over here I have my test function, and I'm summing it over these zeros, and I've got a little bit of a weight coming in. And then over here I've got a sum of a prime squared, prime cubed, prime to the fourth, etc., etc., etc. But notice I have higher and higher prime powers here, p to the 1/2, p to the 3/2. Well, once I get p to the 3/2, the sum of 1 over p to the 3/2 converges. It's dominated by the sum of 1 over n to the 3/2. And the log p over log n, that's going to be fine. So all those terms I can just gobble up together as an error term. And all that really matters is the sum over the primes and the prime squareds. If I just put in absolute values, I'd be in trouble. 1 over p diverges. And 1 over square root of p really diverges. But there'll be cancellation. You can look at cuspidal new forms, which is something we'll be looking at later this summer. And you get a nice formula like this. And again, the higher order terms don't really matter. All it comes down to is studying the first and the second. If you've seen the central limit theorem, this should become reminiscent. It's the first two moments that control what happens. The higher moments control the rate of convergence. It's the exact same thing going on here. So this is the perspective I've added to the subject of how you should be viewing these calculations. I'm not going to go too much into the different statistics. There's something called the n-level correlation. It's asking if I have a sequence of events, how often will their differences be in a certain box? This is what Montgomery started looking at first. And this is where, he showed it to Freeman Dyson, and this is what we see in random matrix theory. This is what we see looking at nuclear physics. If you know all the correlations, you know the spacings between events. But it's hard to know the correlations in full generality. We typically can only evaluate them in some kind of restricted window. So it turns out we have a lot of results. So the first is Odlyzko's numerical results that the spacings between zeros look like the spacings between eigenvalues. We have Montgomery's work on the two-level correlation, and then Dennis Hedgel, about 20 years later, was able to do the three-level correlation. And these are difficult calculations. It takes a while to figure out what's the right object to look at. Around the same time, Rudnick and Sarnak did the n-level correlation not just for the Riemann zeta function, but for all cuspal automorphic L functions. And they showed if you take suitably restricted test functions, number theory and random matrix theory agree. And this was remarkable. And this was providing a lot of evidence that if we understand complex Hermitian matrices, we understand number theory. But then they realized that this is not the whole story, that there's a lot of things that have the same answer. One of my favorite jokes is about the classic professor who spends his entire life trying to prove that the Iliad and the Odyssey were not written by Homer, but by another blind deaf Greek of the same name. You can have different things that have exactly the same behavior. So it turns out it's not just complex Hermitian matrices that have the same behavior when you look at zeros high up. The classical compact groups, the subsets, the subfamilies of unitary matrices have the same behavior. So when you're saying zeros of the zeta function look like complex Hermitian matrices, you could also say they look like unitary matrices. They're different families, but they have the same behavior when you go very far up on the critical line. So the real question is, what really describes what's going on? So the problem is these statistics are insensitive to finitely many zeros. And there's one place where we really care about what's happening. So what's that one place for number theory that we care about what happens? The central point. These n-level correlations and these spacings between adjacent zeros, you can throw away everything that's going on near the central point and it's not going to change the limiting behavior. And that's the point we care about most. So this is not the only statistic to look at. So Ivanets, Luo, and Sarnak introduced a new statistic called the n-level density. And what's nice about this statistic is it now depends crucially on what's going on near the central point. So now I have my test functions, they're Schwartz functions, so they have rapid decay, they're differentiable, their derivatives have rapid decay, and I'm going to sum their scaled zeros. And so for each form f in my family, I can calculate this, and then I can average over all forms in the family. One of the things you might notice is the subscript here is I'm summing over distinct indices. So really what we want is we want ji is not plus or minus jk. It's just this is what leads to a really nice combinatorial expression, and that gets you the determinant expansions that Katz-Sarnak get. Could you look at this where you allow repeated indices? Of course. Any thoughts how you would handle that? So if you know the answer when the indices are distinct, how would you get the indices when they're repeated?
Split it up.
Okay, what's the name of the technique you would use? Use this technique a lot in combinatorics or probability. Inclusion, exclusion. Right? So if I want to figure out what's going on when some of them are repeated, well, I can just put those in and just add and subtract the contributions. It's just bookkeeping. And a lot of the subject is bookkeeping, so it's worth emphasizing when you need to do stuff like this. You want something that will be tractable at the end of the day. All right, so now individual zeros contribute, and because my functions are Schwartz, they're rapidly decaying. Most of the contribution is going to be from the zeros near the central point. Hey, that's great. That's the point we care about most. This is the statistic that's designed for that stuff. And now we just average over families, over similar elements in a family. And the Katz-Sarnak conjecture is for a nice family of L functions, the n-level density depends only on the symmetry group attached to the family. So essentially the idea is the following. We form the one-level density for a specific element in our family. Maybe we look at all L functions whose conductor goes up to n, or maybe whose conductor is size n. We divide by the number of forms in the family. And then the hope is that as n goes to infinity, this converges to integrating our test function against a nice function that depends only on the symmetry of the family. Okay, so the different families, we have SO even, SO odd, orthogonal, we have symplectic, we have unitary. And they have different behaviors. So the 5 families all have different behavior near the center. And eigenvalues of matrices at 1 behave like zeros of L functions at 1/2. The problem is the 3 orthogonals, while they're different, you can only see the difference if your test function lives beyond -1, 1. So if the Fourier transform of your test function is 0 outside -1, 1, the 3 orthogonal flavors look the same. What this means is you could have the ridiculous situation where you have an L function where all the signs are even, but it behaves like SO odd. It behaves like an odd-signed family. It turns out this actually does happen for one family. I was extremely careful in how I phrased things in my thesis, and so when one of my colleagues found something like this, my thesis was not wrong because I was very cautious in how I phrased things. You know, it seems absurd to have something like that, but it could happen. Okay, and so here's the similarities, and I've talked about this yesterday, between nuclear physics and L functions. In number theory, we have zeros. In nuclear physics, we have energy levels. In nuclear physics, we shoot a neutron. In number theory, we shoot a Schwartz test function phi. In physics, we have the energy level, and in number theory, we have the support. You know, where does our function live? We would love to shoot a completely localized delta spike. We can't. That's essentially equivalent to shooting something with infinite energy. We do not have that technology. So it's nice to have a physical interpretation of what you're doing. All right, so quickly some results. There's a bunch of families where we can show agreement between number theory and random matrix theory. I'm not going to really go into too much of the results here. One of the applications of this is bounding average rank. As we talked a little bit about this yesterday, if my function is non-negative, I can throw away all the zeros except the ones at the central point, and then I get an upper bound for the average rank times phi of 0. And then the goal is to figure out what phi can you put in here to get this quantity on the right-hand side to be as small as possible when you divide by phi of 0. So looking at the n-level density, we actually get a decay rate of zeros at the central point, you know, of rank r or higher, decays like r to the minus n. So the higher level density you calculate, it looks like the better. The problem is you get a constant here that depends on n. So for instance, if you want to look at how often do you have vanishing of order 3 or higher using the 2-level density, you might actually get a bound that's over 100%. And you might get, you know, at most 187% of the forms vanish to order 3 or higher. It's a true statement. It's also useless. I can prove at most 187% vanish to order 3 or higher a lot faster. But when you start increasing r, this becomes better. The multiple zeros at the central point reinforce each other. And now you start going, you know, what if I want to have vanishing order 5 or 6? Then you get a better result than you get with the 1-level density. Unfortunately, we really don't expect to have such high vanishing, so in some sense this isn't that great, but it does give us better estimates as you go higher and higher and higher. The 1-level density gives you, it drops off like 1 over r. This gives you, it drops off like 1 over r to the n. Okay, so let's go through an example really slowly and show how you would calculate n-level densities. Let's look at Dirichlet L functions. So this is going to be the prototype of a calculation you would do. So to make things easy, I'm going to assume my characters have prime modulus. So my groups Z mod MZ star, they are going to be cyclic groups. There's going to be some generator. I think I call that generator G. And so zeta m minus 1 is going to be an m minus first root of unity. Okay? And then the trivial character just sends k to 1 if it's relatively prime with m, and 0 otherwise. And so these are periodic. If I change k by adding m or 2m or 3m, I don't change the value. There are m minus 2 primitive characters that are not trivial, and because it's multiplicative, their value is completely determined by what they do to the generator g. And it turns out what they could do is they could take g, they could square it, they could cube it, they could raise it to the 4th power. And so there's a really simple classification for what's going on. So again, in a talk like this, the goal is not to understand and follow everything line by line by line, but to get a sense of what would you do, how are these calculations being done. This is a little bit misleading because things are so nice here. I can be so explicit in everything that's going on. Most of the time, you're not going to be able to have formulas this nice, but walk before you can run. And so if I want to calculate, what does calc to L do? It takes, if k is g to the a, it takes g to the lth power of my primitive m minus first root, and then this just raises it to the lth power. Okay. So let's form an L function. So chi is going to be our character. We can look at these sums. These are Gauss sums. It turns out they're of size square root of m. There's lots of really nice proofs of this. The difficulty is not showing that it's the size square root of m. It's determining what is the sign in front of it. I'm not going to get into that now. We form an L function. It has a product like this. So for the Riemann zeta function, there was no chi of p. It was just 1. Not a big change. You can complete the L function. The completion depends a little bit on whether or not chi of minus 1 is 1 or minus 1. Not a big deal. And then we have our explicit formula. We relate our sums over our zeros to our various expressions here. And again, all that matters is the first two moments. The higher moments are lower order term. All right, so now we want to calculate what's going on. The nice thing is we have a finite sum over characters. We can pass that through the primes and hit it over here. What's very nice is that when I have my test functions, when I have my explicit formula, all of these test functions are normalized the same way. I rescale them all the same way. If the scaling depended on the form, I could not pass the sum over the family through the test function. Dirichlet characters are very nice like this. Cuspal new forms are very nice like this. Families of elliptic curves are not. And it's an enormous amount of work to pass this through. There's a lot of technicalities here. This is one of the reasons why I now have a PhD, is my thesis was handling a lot of those painful technicalities. All right, so we want to calculate what's the sum of all characters in our family. Well, it turns out it's equal to m minus 1 if k is 1 mod m and 0 otherwise. The simplest way to see this is if k is 1 mod m, every character sends it to 1. All right, so we just count it then m minus 1 times because it's m minus 1 characters. If it's not 1, then there's some games you can play and you just show that it averages to 0. Okay, so continuing, we're summing over all characters that are not principal. We're removing essentially a multiple of the zeta function, so we have to remove 1. And the question is just what's the best way to write it? I like to write it as negative 1 plus m minus 1 if p is 1 mod m, and negative 1 otherwise. So each term always has a negative 1, but if your prime is 1 mod m, you have this extra m minus 1 factor. So that way I've always got a minus 1. I can now put this in, I substitute, and I have two sums to look at. And this is just looking at what's going on at the primes. So I have the sum of all primes where I'm having my negative 1, and then I have this extra factor of m minus 1 whenever my prime is 1 mod m. So if you look at this, the hope is that this is going to be small. The primes go up to m to a sigma. So as long as sigma is not too large, we get to divide by an m minus 2. We should be okay. We have a p to the minus 1/2. Well, when you sum that, you should get a p to the 1/2. So this should become like an m to the sigma over 2. We're dividing by an m. If sigma is less than 2, we have a higher power in the denominator than we have in the numerator, and it should be 0. So basically, you should be able to get up to sigma a little bit less than 2 over here. For this one, it's a little bit harder, because we have a sum over primes that are 1 mod m. Oh crap, this is of size 1. But most primes are not going to be 1 mod m. The hope would be basically just 1 out of every m primes. And so you would hope that there would be like a depression. So we can break it up into two possibilities. So here's the first one, and we talked about why this is small. And now we want to show that this sum is small too. Anybody have any thoughts as to why this sum might also be small? So we're summing over primes that are 1 mod m. Because the problem is if I have a small prime, that's going to contribute. It's not going to go to 0 with m. So again, look at the indices. Look at the sum. It's over all primes congruent to 1 mod m. What can you tell me about a prime that's 1 mod m? It's what? It's at least 2. What's the smallest prime? What's the smallest number that could be prime that's 1 mod m? M plus 1. Right? 1 is not prime. P is 1 mod m, so the possibilities are 1, m plus 1, 2m plus 1, 3m plus 1. So the very first possible prime would be m plus 1. So I don't have to worry about having a very small prime. The smallest prime I could get is m plus 1. So what you can do is you can actually bound the sum. I know it starts at m plus 1. And that's going to give me an extra factor of 1 over m. Yes?
So how do you go from, all these business with logs and test functions, and you just essentially can ignore it?
Well, I'm just doing an estimate. The log of p over the log of m, we know p is at most m to the sigma. This is going to be sigma log m. So sigma log m over pi, that's going to be roughly at most of size sigma. So I'm just doing upper bound. So the double less than just means up to some constant.
And then with the test function?
So the test function, it's Schwartz, it's a rapid decay, it has a maximum value.
Oh, okay.
So for a lot of these calculations, we're being very crude right now. And so because we just want to show that this is 0 in the limit. So most of the families, it's not going to be this easy. Everything is small. But if sigma were now larger than 2, now we would need to do a lot more work. And so then there's games you can play. I'm not going to go through this. It's on the slides as to how you would handle that. We now have to handle the second sum. That's now summing chi squared. Well, again, we have explicit formulas. We can see what that is. I'm not going to go through the calculation. But if you want to see it, it's here. You again play the similar trick, but now we have p could be plus or minus 1. Well, fortunately, what's the smallest prime that's minus 1 mod m? It's m minus 1. So again, you wouldn't get something until you're far down. It's again going to be small. You could then try to generalize things and say, well, what if we don't have a prime modulus? What if we have a general modulus? And you can play all these games. It gets a little bit more involved. One of the things that's nice now is, when we start going through all the different work, let me go through it. But essentially what it comes down to is you've got a lot of congruences. And at least one of them is going to force your number to be of size at least square root of m for things to work. So you can't get anything too small coming into play. We're not really going to be looking at families of Dirichlet L functions, so I'm not going to go into too much detail here. I just wanted to give you some sense. Okay, and so I'm going to skip those, but you can at least hit pause if you really care about that. All right, so what I will do now, no, keep it going, because I'm going to switch to part 2. So I'm going to leave the clicker over there. Now this is part 2. Okay, so for part 2, I now want to start looking at compound families. I want to look at more involved things. I think I'm going to skip the compound families. This is how you would try to predict what the symmetry of L functions are. I will just have the slides here, so you can always hit pause if you really want to see what this is. I think I've recorded this lecture somewhere, but there's a lot of theory that we've been able to develop to predict what the symmetry group should be. All right, I want to talk about the cuspidal new forms, because this is the project I really want us to continue. So Ivanus-Luosanic's paper, they look at cuspidal new forms and they look at symmetric powers of cuspidal new forms. Right now we don't really have to worry what the symmetric powers are. And so we have a modular form. So we talked a little bit about this yesterday. I have sets of matrices A, B, C, D. They can act on complex numbers. And I can look at families of matrices that have nice transformation properties. So here I want the entries to be integers, I want the determinant to be 1, and I want C to be congruent to 0 mod n. So it turns out if you take two matrices of this form and you multiply them together, you get another matrix of this form. So it forms a group. And we can look at functions that transform nicely under matrices in this group. So if I take a matrix in this group, I can look at my function f of gamma z, and I want it to equal cz plus d to the kth power times f of z. So think of this as a generalization of periodic functions. Periodic function, f of x plus 1 is f of x. I'm transforming x by 1. Here now I'm allowing myself to have, it doesn't have to be identically 1, and it can be more than just a translation by 1. There's got to be a very nice factor. I have a Fourier series expansion. I have an L function. It turns out I also have an Euler product. I have a norm on this space. I can multiply by a function f by g. I have to multiply by a power of y. I integrate over the space. This is the fundamental domain. So we talked about the fundamental domain last time with the circle, and this part over here we talked about tessellating and translating and covering the plane. I just have to integrate over that one region. And then, as always, there's the theory of normalization. How do you want to scale things? And so there's a certain scale here. If you're going to work on this subject, then you have to look very carefully and see what the scales are. Here is the beautiful thing, the Peterson formula. So I have my scaled Fourier coefficients. I fix a form, and I take two different ones, m and n, or maybe they're the same. I take the complex conjugate of the second one, and the Peterson formula says if I average over all forms in a basis, then I get delta mn. This is the Kronecker delta function. It's 1 if m equals n and 0 otherwise. And then I have a Bessel function and a Kloosterman sum. These are not pleasant to work with, but it could be worse. It's at least an explicit formula to work with, and for certain regions this actually doesn't contribute. In other regions it does contribute. So now we do the explicit formula as before. We take our test function, we sum over the scaled zeros, we average over all elements in our family, and we get a sum over primes and prime squareds. It turns out the prime squared is very easy to do, and we're just left with the sums over primes.
Just to go back to this Peterson formula.
Yes.
So you said sometimes it contributes, sometimes it doesn't.
So if the support is sufficiently small, it doesn't contribute. If the support becomes larger, it contributes.
But is the main idea is that, for the most part, we should think of this delta as, or the triangle as the...
The hope is that this is the main contribution, is the delta part. But unfortunately, the Bessel-Kloosterman piece can't contribute. Now what's nice is it contributes positively for the forms with even sign and negatively with the forms for odd sign. So if you look at the family where you don't split by the sign of the functional equation, they actually cancel and you don't have to worry about the term. If you want to split by sign and say, well look, I care just how the even forms behave by themselves, then you have to worry about this form. And that's where the sum gets a little bit more involved. So it turns out that the Fourier coefficients have a lot of nice properties. There's two different ways to normalize. You can normalize so that the Peterson norm, when you integrate over the fundamental domain, is 1, or you could normalize so that the first coefficient is 1. Depending on what you're doing, one normalization is better than the other. I like to normalize so that the first coefficient is 1, because then you get this beautiful multiplicative property. Lambda fm, lambda fn is the sum over d dividing the GCD of m and n of lambda fmn over d. It turns out if your form is square-free level, you have an explicit formula for the sign of the functional equation in terms of the Fourier coefficient at the level n. It's wonderful. This does not hold sadly if the level is not square-free, and that has really hurt us in one of our sequel papers. What this allows you to do is it allows you to split by even and odd forms very nicely. Look at 1 plus or minus epsilon f. If epsilon f is 1, you get 2. If epsilon f is minus 1, you get 0. So this gives you a double count for all the even forms. If you looked at 1 minus epsilon f, it double counts all the odd forms and doesn't count the even forms. All right, so then just divide by 2. So it allows you to look at a related sum, and it will also involve the Fourier coefficients, and that will get you a split over even and odds. So we have Riemannian sums, there's lots of sums. This is the big result from Arrhenius-Leroux-Sarnak. It handles the Bessel-Kloosterman terms. Over here, this is related to the Kloosterman sums. I don't really want to get into all the details now. I just want to show you they found a formula for a closed form expression for the Bessel function times times Kloosterman stuff. They found a way to handle the Peterson stuff. And they get this beautiful answer at the end of the day. You can see that there are so many sums here that you do not want to look at the generalization of this to n dimensions. They did it in one dimension. I want to take whatever I have and I want to make it look like what Arrhenius-Lewis-Sonic did and not have to worry about the n-dimensional analog of this. So to get limited support, we have the Kloosterman sum. It turns out you have a nice bound for the Kloosterman sum. You have nice bounds for the Bessel function. You have bounds for the Fourier coefficients. What this is essentially saying is bound everything crudely, assume there's no oscillation, there's no cancellation by sign, put in these weak bounds, and you can get support up to a certain range without any trouble. You expect to be able to do better because you expect, well, there's oscillation, it should cancel. And so then you try to increase the support, and now you have to handle terms like this. And what you can do is you can use Dirichlet calculus to split the Kloosterman sums into primes in arithmetic progression. You can use the Riemann hypothesis to count how many primes there are. All that matters is what the primes are congruent to. There are techniques to handle stuff like this, and we can get up to support of 2. We can then talk about trying to increase the support. This is where we would get hypothesis, S and T. I really don't want to go into too much detail right now, but this gives you a sense of the kinds of terms you would look at. Here's the main idea. Let's say we want to look at the 2-level density. So now we have a product of phi hat at 2 different places. How do we handle this? Well, we now have a Bessel function involving 2 things here. Arrhenius-Lewis-Sonic did it with 1 thing. But if you notice, there's a really simple change of variable you can do. So this allows us to use Calc 3, the Jacobian, the change of variable formula. Most of the time my students flee in horror when this fact is recalled, because this is usually not done well in Calc 3, but we have formulas for change of variable. And so make the following change of variable. Let U2 be the product, let U1 be just x1. So x2 is U2 over U1, x1 is U1. Why is this nice? Notice I have the log of x1, the log of x2. When I plug this in, I'm going to get the log of U1, the log of U2 minus the log of U1. If you've taken probability, you will see in a moment that this is a convolution. And this is going to allow me to do one of the integrals very nicely. Also now the x1, x2, that just becomes U2. So now I have just one variable in my Bessel term. And it's looking a lot like Arrhenius-Lewis-Sonic. The difference is now I have 2 phi hats, and I now have an integral over U1, but there's no U1 dependence here. But there's a U1 over here. All right, so I've got to put all this together. So when you do the U1 part, and I do a change of variables, let's let W1 equal the log of U1. The derivative of, what's the derivative of log of U1? 1 over U1, that's the U1 down there. It goes away when you change variables. And now I get phi hat of W1, phi hat of log of U2, log minus W1. This is just the convolution of 2 functions. So this is just a well-defined operation. You give me a function phi hat. This gives me a new function. It's a function just of log of U2 over log of I. I'm just integrating out W1. The way this occurs in probability is if you want to calculate what is the density of the sum of 2 independent random variables. Let's say this is the density of the first, this is the density of the second. I want to calculate what's the probability I take on the value of log U2 over log R. Well, if the first one is W1, the second one must be what I want minus W1, so that when I add them together, I get the quantity I want. So this occurs all the time in probability theory. It gives you the density of a sum of 2 independent random variables. And so now I have, when the dust settles, exactly what Arrhenius-Lewis-Sonic looked at. The only thing that changes is now my test function is the convolution of 2 test functions. If we could do it for 2, we can do it for, for 3 or n. So here's for, what would go on with 3? You want x1, x2, x3, x1, x2, x1, and you now have a triple convolution. And so you get some function C3. And so the difficulty now is we don't get things that look like the determinant expansion. Things look a little bit different, and now we have to do some combinatorics to break things back out. And so the idea, and this has already been done, the combinatorics has been completely resolved. All that's left now is just matching things with number theory. I'm not going to go into too much detail. What I want to just say is that in the new formula, you have terms that almost emerge as the support gets larger and larger and larger. And I want to just give you a quick rough sense on where it's coming from. So I'm going to skip a lot of this, these estimates. Okay, the new Riemann matrix theory results. So we basically have a lot of combinatorial sums, and it turns out that there are formulas for stuff like this. And so here chi is an indicator function, and I want this sum to be less than or equal to 1. And the epsilons are going to be plus or minus 1, the etas are going to be plus or minus 1. And when you look at something like this, if all the y's are very small in absolute value, then I don't really care what's in front of them. If they're all very small, there's no way that this can break 1. That's going to be trivially true. So if all of the y's are at most 1 over n, and I have n of them, the sum can't be greater than 1. So in that case, I know that this is going to just give me 1. Now, what if the y's could be a little bit larger? Well, if the y's could be a little bit larger, crap, now I have to worry about something like this. What if the y's could be as large as 1 over n minus 1? Well, I have n terms, and if they all perfectly align, I could get something as large as n over n minus 1 that exceeds 1. Crap. What's the only way, if they are all of size at most 1 over n minus 1, that I could exceed 1? They all have to have the same sign. Because if one of them has an opposite sign, there's going to be some cancellation. And since I only have n terms, if each one is at most 1 over n minus 1, let's say I have n minus 1 that are positive. And the best case would be for the negative one to be essentially just below 0. Well, then the largest the sum could be would be n minus 1 times 1 over n minus 1, which would be 1. So if even one of the terms is of different sign than the others, I don't have to worry about breaking 1. So all I have to worry about is all the signs are positive except one sign is negative, or all the signs are negative except one sign is positive. And now I can handle up to 1 over n minus 1. Okay, now what if I want to handle up to 1 over n minus 2? How many if I have how many positive signs and negative signs, what would be the split?
And you're still requiring y to be 1 over n.
Well, now y could go up to maybe 1 over n minus 2. How many positive signs can I have and still have a contribution? I could have all of them positive. I could have n minus 1 of them positive. Could I have n minus 2 of them positive? If n minus 2 are positive and 2 are negative, those two negatives will pull me down and I'll be below 1. And then if I went up to 1 over n minus 3 for the values of y, you can see the new terms emerging. So that's the advantage of this expansion. That depending on how far you want to calculate the support, you can see the new terms emerging as you go further and further down. And so that's really all I want to say about the stuff like this. This gives you an understanding of what the key idea is, what are the pieces of the puzzle. The random matrix theory has already been done. We have the terms that have emerged. We now have to just clean up the number theory and show that it matches. And I want to try to find out what number theory do we need to increase the support. I don't have it on these slides. I have it in other talks I've given. When you look at the Dirichlet L functions, we talked about how you could get support up to minus 2, 2. What if you want to go further than minus 2, 2? It turns out this is related to interesting questions about the distribution of primes in arithmetic progressions. And there's a lot of wonderful conjectures. And Montgomery has a beautiful conjecture about how the error term should be distributed in the different congruence classes. We are not even close to being able to prove anything like this. So I'll try to do this on the blackboard. So let's see if I can slide down. So this is the philosophy of square root cancellation. So is it seeing me if I'm over here? Okay. So if I have a bunch of objects that are of the same absolute value, but the signs are random, you expect the sum to be roughly of size square root the number of terms. So if you flip a fair coin, let's say it's 1 if it's a head, minus 1 if it's a tail. On average, if I flip it n times, what should my sum be? 0. And my fluctuations should be of the size square root of n. This is the standard deviation. All right, so how would that help us here? Well, let's say we know the prime number theorem, and I'm going to lie up to logarithms. I don't really care about logarithms. The number of primes up to x is about x over log x. And an error is roughly of size square root of x. I'm not worrying about logarithms. All right? Everything's is true up to logarithms. I want to now distribute primes in congruence classes. So let's let Q be a prime. So Dirichlet showed that the number of primes congruent to A mod Q that are at most x is basically the number of primes divided by phi of Q, where phi of Q is the Euler-Toscan function. It's the number of numbers relatively prime to Q. Well, since Q is a prime for us, that would just be Q minus 1. And then the question would be, how would the errors be distributed? So I've got something of size square root of x. And I've got to put these errors among these different congruence classes. So some congruence classes could have a few extra primes. Some congruence classes could have a few fewer primes than this quantity here. So I want some error term plus some error that depends on A, Q, and x. The number of error terms I have is Q of them times the size is going to be of size square root of x. But it's not the average size, because I can have cancellation, because sometimes I'll be high, sometimes I'll be low. So I expect square root cancellation. So whatever the size is, I would expect maybe square root of average size. Right? And so now I should be getting like the average size should be, I might be off by I'm sorry? Yeah, and that's too high. So I'm doing, oh, sorry. I'm sorry. I'm doing it the wrong way. It's the square root of Q. It's the square root of the number of terms times the size. Right? So when we flip a fair coin n times, on average I expect to have a sum of 0. And I expect the fluctuations to be of size square root of n, square root of the number of terms. So now instead of having coins of size 1, the coins are of size whatever the average error is in absolute value. And the number of terms I have is square root of Q. So I get that the average size should be roughly square root of x over square root of Q. We expect something like this for the size of the error terms, up to logarithms. Or maybe up to like a Q to the epsilon to just cover your ass. Something like that. This is very close to Montgomery's conjecture. If we were able to get an error of this of like, I think, square root of x divided by, I think, Q to the epsilon for any fixed epsilon, I think we can get infinite support for the Dirichlet L functions. We don't need that much of a savings to push things forward. We don't have a conjecture that's that strong that we can prove. And so I have a paper with Dan Fiorelli where we look at a bunch of standard conjectures in number theory about how primes are distributed in congruence classes, and we use these to get different results as to how far we can push the one-level density, n-level density calculations. If we had something like this, we could get infinite support. There are other ones where we can get support up to -4,4. And it's always interesting to see how much do you need to know about these quantities to get information about larger support. Or conversely, if you happen to know larger support, what would that tell you about these quantities? And this gives you some idea of why people might care about these n levels. It's to provide some support, some evidence for how these things are going. Okay, any questions on this part? All right, let's hit stop.